Welcome to the Architecture of Change, your blueprint for understanding chemical reactions and equations. Matter is constantly transforming all around us. From an iron nail rusting to cooking food, these are examples of chemical changes where the fundamental nature of a substance transforms. The foundation of all chemical reactions is an unbreakable law, the law of conservation of mass. This law states that in any chemical reaction, mass is neither created nor destroyed. The total mass of all substances before the reaction must equal the total mass after the reaction. On an atomic level, this means the number of atoms of each element in the reactants must exactly equal the number of atoms of that element in the products. Now let's explore how chemists communicate these changes using a universal language, the chemical equation. We move from describing a reaction in a long sentence to a concise word equation, and finally, to the most efficient form, the skeletal equation, using chemical formulas like Mg plus O2 yields MgO. However, a skeletal equation isn't always complete. If the number of atoms doesn't match on both sides, the equation violates the law of conservation of mass. This is why we must balance the equation. A truly informative chemical equation does more than just list the components. It provides critical details. We use physical state symbols to specify the state of each substance. S for solid, L for liquid, G for gaseous, and AQ for aqueous solutions or dissolved in water. Reaction conditions like temperature, pressure, or the presence of a catalyst, such as sunlight and chlorophyll in photosynthesis, are written above or below the reaction arrow to give a complete picture. Chemical reactions fall into structural patterns that help us predict their products. Let's look at the four main types. First, we have combination reactions, where two or more reactants form a single product. The opposite is a decomposition reaction, where one compound breaks down into two or more simpler substances. Next are displacement reactions, single displacement, where a more reactive element replaces a less reactive one, and double displacement, which involves an exchange of ions between two compounds, often forming a precipitate. The fundamental driving force behind many chemical changes is the transfer of oxygen or hydrogen, known as oxidation and reduction. Oxidation is defined as the gain of oxygen or loss of hydrogen. Conversely, reduction is the loss of oxygen or gain of hydrogen. Reactions involving both are called redox reactions. Oxidation has real-world effects we see daily, like corrosion, the decay of metals such as rusting iron, and rancidity, where fats and oils oxidize and change their smell and taste. Chemical reactions are not random. They follow an elegant rule-based system that allows us to describe and predict the transformation of matter. These fundamental principles govern the constant change that shapes our world.